Just enjoy and listen to, and have a fun of it.
Hello everyone, just have fun. This is Story Radio Station, and we are kicking off another deep dive. We're here to get you smart, fast. I'm your host speaker, ready to explore the surprising details.
And I'm the expert speaker, here to connect the dots and look at the strategy. It's really great to be back.
Awesome. Now, before we jump in, just a quick reminder, if you like what we do, please hit that subscribe button, give us a like, and turn on notifications. It genuinely helps us keep these deep dives coming.
It really does. We appreciate the support. Thank you.
Okay, so let's talk about today's topic. Recently, we've tackled some pretty big trends, right? GPUs, AI data centers, physical AI, even sim-to-real. Well, today's deep dive is kind of where all those technologies meet and start producing, well, real-world results you can actually see and measure.
Absolutely. It's a technology that's already, turning heads in the global stock markets, a critical growth area. But maybe even more importantly, it has this huge potential to fundamentally boost safety and efficiency across society. Think supply chains, critical infrastructure.
Okay, so the big reveal. We are diving into digital twin technology today. Now, digital twin, it sounds straightforward, maybe like just a digital copy, but what's the real strategic punch behind that name?
Well, at its core, a digital twin is a virtual replica of something physical, an asset, a system, a process. But the key phrase you mentioned earlier is real-time. That's crucial. It's not just some static, fancy 3D picture.
Right. That's the big leap, isn't it? We're going beyond just looking at a model. We're building this living, breathing, virtual copy of the twin where we can run simulations, predictive analysis, basically actively fine-tune the real thing.
And what's really fascinating is the history. I mean, the basic idea actually came from NASA back in the 1960s, initially for managing spacecraft, things far away.
Wow, okay.
But today's digital twin is way more advanced. It takes those static models, maybe from BIM or CAD designs, and injects live IoT sensor data, plus external stuff too, like business information, to create something truly dynamic and contextual.
Okay, so if it's more than just a 3D model, what exactly is it made of? Let's break down the mechanics. You mentioned layers, the key parts that make this a living system, not just a blueprint.
Yeah, you can think of it like maybe a 4-layer cake. Starting at the bottom, layer 1 is the physical modeling layer. This is where you create that accurate, static 3D replica.
So using existing plans, CAD files.
Exactly. BIM, CAD data, but increasingly also really precise scanning tools like drones and LiDAR scanning.
LiDAR, that's this laser tech, right?
Yeah.
Measures distance super accurately for a detailed 3D map.
Precisely. That gives us the accurate shell. Then moving up, the second layer is like the DT's lifeblood, the data integration and synchronization layer. This is where the real-time magic happens.
Okay.
We pull in live data from all those IoT sensors on the physical object, but crucially, we also blend in external business data, things like market prices, weather conditions, maybe even local traffic patterns. It captures the whole context of how it operates.
So we've got the accurate body, the live data flow. Now we need the brains, I guess.
That's layer 3, the analysis and simulation layer. This is where the serious computing power comes in. We use AI and machine learning models to crunch all that data, run complex simulations, predict what's going to happen.
And the final layer, the top layer of the cake.
Yeah.
This must be where the value really comes out.
Absolutely. Layer 4 is the visualization and application layer. This gives stakeholders the big picture, but most importantly, it delivers what's called prescriptive analysis.
Prescriptive analysis.
Yeah.
So, okay, what does that mean exactly?
Well, if predictive analysis tells you, say, this pump is likely to fail next month, prescriptive analysis goes further. It uses the data to tell you what to do. Like, you need to reduce the pump pressure by 15% right now to extend its life by 6 weeks. It gives you the specific action.
Ah, okay. So it's not just warning, it's guiding. That totally shifts things from reacting to, well, proactively managing.
Got it. So now we know the structure. Let's talk strategy. You mentioned DTs can be categorized, right? Based on how complex they are. Yes. Typically into 3 main types, sort of scaling up in complexity. First, the simplest is the asset twin. This focuses on just one single component, maybe a specific engine, a wind turbine, a piece of factory equipment. The goal is optimizing its performance and predicting maintenance.
Makes sense. One thing at a time. What's next?
Then you scale up to the process twin. This models a whole workflow or process. Think an entire manufacturing line or a complex supply chain. Here, you're looking for bottlenecks, ways to improve the overall flow and efficiency.
Okay, from a single part to a whole sequence of operations.
Yeah.
And the biggest scale.
That's the system or city twin. This models massive, complex systems, an entire city, a major port, an airport. This is for big picture decisions, large-scale risk management, like, say, planning for disaster prevention or optimizing citywide traffic. That virtual Singapore project is probably the most famous example of a city twin.
Virtual Singapore. I remember reading about that. Sounds amazing, but I also heard there was a catch.
There was. While it was a technical success, the project became heavily dependent on one specific company's technology Dassault systems in that case. This vendor lock-in became a real issue later, driving up costs for updates, changes. The long-term flexibility suffered.
Ah, the hidden cost of being logged in. That makes sense.
It really does, and that's why standardization is becoming so critical in the DT space now. Adopting open standards like the IEP 2888.3 standard ensures different systems can talk to each other. It's a strategic move, really. It gives you flexibility and drastically reduces
Good evening, and welcome to the Story Radio Station, where we explore tales from around the world.
tech to become an expensive trap. 10 seconds plus.
And welcome back to Story Radio Station Part 2. Before the break, we unpacked the 4 layers and 3 types of digital twins, and importantly flagged why standardization is so key for the long run. Now, let's get into the engine room. What actually powers these twins and makes them react instantly to the real world?
Okay, the absolute essential piece of the puzzle here, especially dealing with all that data volume and the need for speed, is edge computing.
Edge computing. Okay, let's quickly break that down for anyone unfamiliar. What is it, and why is it so vital for DT?
Right. So edge computing basically means processing data right where it's generated out at the edge of the network near the sensors instead of sending absolutely everything back to a central cloud first.
Okay, processing locally.
Exactly. And this is non-negotiable for what we call mission-critical environments. Think about a smart factory floor or maybe that river monitoring system we mentioned. If there's an equipment failure about to happen or a flood warning, you need instant alerts and potentially instant control actions. You can't wait for data to travel to the cloud and back. Minimizing latency, that delay time, is absolutely critical for safety and keeping things running smoothly.
That instant feedback loop really is the game changer, isn't it? Plus, I imagine processing data locally means you don't have to send everything to the cloud. That must save costs, too.
Oh, absolutely. It filters the noise, processes the urgent stuff right away, and only sends necessary summary data or specific alerts centrally. It dramatically cuts down on cloud bandwidth and storage costs. It's a win-win. Faster response and cost savings.
Okay, so Edge handles the immediate processing. But for the DT to do that complex prediction and prescription we talked about, it needs some serious computational muscle, right?
Definitely. And that brings us right back to high-performance computing, HPC, and specifically GPU-based accelerated computing.
See, I knew our GPU talks would connect back here.
They absolutely do. Companies like NVIDIA, with their Omniverse platform, are partnering with industrial giants like Siemens and their accelerator platform. They're essentially building the infrastructure for the industrial metaverse.
Yeah.
You need that massive parallel processing power that GPUs provide to run these incredibly complex physics-based simulations in real time.
And the scale they can handle now is just mind-blowing. I saw a case study about HD Hyundai. They built a digital twin of an entire LNG carrier. We're talking 7 million individual parts visualized and simulated.
7 million.
Yeah.
They used it to verify the whole ship virtually before they started building, which massively sped up the process and cut down the risk of costly manufacturing errors on such a huge, complex asset.
Imagine catching a design flaw in a 7 million part assembly virtually versus finding it after you've started welding steel. The savings are enormous. Now, speaking of terms, we often hear digital twin mentioned alongside things like smart twin or sim to real. It's worth quickly clarifying the differences.
Good point. So, we established the digital twin is primarily there to help humans make better decisions based on data. How does a smart twin take that further?
The smart twin is the next evolution. It uses more advanced AI and machine learning, not just to predict, but to actually learn and autonomously optimize its own performance. It can make certain self-directed, autonomous decisions to improve things without waiting for a human command. It's starting to close the loop itself.
Okay, so more autonomous. And sim to real, S2R. That sounds related but different. It is related, but the focus is narrower. S2R is mainly a methodology, often used in robotics and AI training. It's focused specifically on the challenge of training an AI model in a simulation, the sim, and then making sure it works correctly when deployed in the messy, unpredictable, real world. It's about bridging that simulation to reality gap, for AI behaviors.
Got it. Different tools for different jobs. Okay, let's get to the bottom line then. What's the actual payoff? How much value, economically and socially, are these digital twins creating? Any hard numbers?
The biggest economic win is definitely minimizing unexpected downtime. That costs industries billions. We found a great example. A port terminal here in Korea implemented a DT-based control solution. The result, they measured a 65% improvement in productivity.
65%. That's huge.
It's massive. And when you can point to ROI figures like 65%, digital twin adoption shifts from being maybe a cool experiment to an essential industrial tool. It's becoming a must-have.
I can see why. And beyond the economics, there's the social side too, right? Worker safety, public services.
For sure. Remotely monitoring equipment or hazardous environments keeps workers out of harm's way. And in the public sector, think about those river monitoring systems providing early flood warnings or optimizing city services based on real-time data. It directly contributes to public safety and disaster prevention.
Looking globally, we mentioned Singapore's success, but also their vendor lock-in issue. How are others approaching it?
Well, the UK, for instance, with their National Digital Twin program, took a different path. They're heavily focused on establishing those interoperability standards and clear data governance rules first, before building out massive single platforms. It's a more federated, standards-driven approach, aiming to avoid the exact lock-in problems Singapore faced. Different strategies, same goal of optimization.
And thinking about the stock market angle we touched on earlier,
Yeah.
the more complex these DTs get, the more compute power they need. This must be driving huge demand for the underlying tech.
Absolutely. It's a direct structural benefit for the infrastructure providers. The need for real-time complex simulation is a massive driver for GPU manufacturers like NVIDIA and the build-out of specialized AI data centers. DT is a core application pushing that whole ecosystem forward. So the market's definitely maturing. We're moving past the stage of just pilot projects or proofs of concept. Companies are now demanding and getting quantifiable return on investment, ROI, like that 65% productivity number. It's spreading rapidly in areas like smart factories, digital healthcare, places where the value is clear. DT isn't just nice to have anymore, it's becoming essential industrial infrastructure.
It really feels like the technology that finally bridges the gap between OT, operational technology, the physical machines and control systems on the factory floor, in the field, and IT information technology, the data and analytics side.
Exactly, it's the convergence point. And the ultimate goal, looking ahead, is that evolution towards the smart twin, fully autonomous, AI-driven operations.
Okay, this has been incredibly insightful. To wrap things up, if someone listening is thinking about exploring digital twins for their own organization, what are the key strategic takeaways?
Based on everything we've discussed, I'd offer 3 main points. First, prioritize open standards. Seriously, consider adopting standards like IEP 288.88.3 from the start. Learn from Singapore's experience, avoid vendor lock-in to manage your long-term costs, and maintain flexibility.
Good advice. Number 2.
Second, invest strategically in GPU infrastructure. To really unlock the predictive and prescriptive power, you need that accelerated computing. Building or accessing a robust AI data center environment with GPU capabilities should be a top infrastructure priority if you're serious about advanced DT.
Makes sense. You need the engine. And the third takeaway.
Third, expand incrementally based on ROI. Don't try to boil the ocean. Start perhaps with an asset twin for a critical piece of equipment where you can clearly measure the benefit, like hitting that 65% productivity gain or reducing downtime significantly. Use those proven results to build the case for expanding to process twins and then eventually maybe even system twins, phased approach.
Excellent. Start small, prove the value, then scale up. All right, that brings us almost to the end. But before we go, we always like to leave you, our listeners, with a final thought to chew on.
Yeah, so here's your homework. If you were to apply a digital twin, even just conceptually, to your own work, your organization, or maybe even some complex process in your daily life, what would be the single most valuable quantitative benefit, that specific, measurable improvement you'd aim to achieve first? What number would you chase?
Something to think about. Thank you so much for diving deep into digital twins with us today. We hope you found it valuable, and we look forward to seeing you on our next deep dive.
And one last time, please do subscribe, like, and hit those notifications. Thanks for listening.